The average rate of change tells us how much the function changes between two values of x. It is the slope of a secant line that connects 2 points on a graph, which is found using rise over run, or change in y over change in x. A secant line goes through 2 points on a graph and shows the average rate of change between them. Once you have the slope of the secant line, you can use the point slope formula to then get its equation. The average rate of change is one of the foundations of calculus, and it leads into instantaneous rate of change, while secant lines lead into tangent lines. The instantaneous rate of change is the rate of change at a single point, representing the slope of a tangent line. It's looking at the rate of change when 2 points come infinitely close together, where the distance between them is effectively 0. It is essentially the average rate of change between two infinitely close together points, resulting in the rate of change at 1 point. It is found by either using the limit definition of a derivative, which is this, where h approaches 0, or just using derivatives. A tangent line touches the curve of a graph at a specific point called a point of tangency, with the slope being the same as the curve at the point of tangency. It is also the rate of change at a point, showing how much something is changing specifically at one moment. Basically, it is a secant line in which the points have been brought so close together that they effectively meet, resulting in the line representing the rate of change at one single point. Using its slope, its equation can be found using the point slope formula. Since the instantaneous rate of change is found by bringing 2 points infinitely close together, it relies on the idea of limits. Limits indicate what value a graph approaches as x comes close to a certain number, regardless of whether the function exists at a point. To contrast, a function tells you the y value at a certain x value, while a limit tells you what y value the graph approaches as you get close to a certain x value. Thus, a limit can exist where a function cannot. For example, even if the function is undefined at a point like 2, 3, the graph still approaches 3 as you get closer to 2, so the limit exists. A limit can also exist from one direction and not the other. This is because the graph may approach a certain y value from the right, but then approach a different y value from the left. When the left-hand limit and the right-hand limit are not equal, the limit does not exist at that point. If it does exist, and it is the same as the value of the function at that point while the function exists at that point, which means there's no math rules broken like dividing by 0, the function is continuous at that point. Using them, we can bring 2 points infinitely close together, which leads to the instantaneous rate of change. This then leads to derivatives, which is an easier way of determining rate of change. Derivatives are a way of finding the rate of change at a point, with them giving the slope of the tangent line of a function. In other words, they are a tool used to determine the instantaneous rate of change of a function at a point. They can be used to find the local maximums and local minimums of a function, and in general are useful when trying to determine how fast something is changing. They are done using the derivative rules, some of which are the product, chain, and quotient rules. Derivatives are based on the limit lim h approaches 0, and then this formula, referred to as the limit definition. Derivatives use limits to find the slope of a tangent line, connecting the rate of change and limits together. Derivatives then allow us to determine critical points and optimize functions. Optimization is when you use derivatives to find the local minimums and local maximums of a function, otherwise known as extrema. Concavity is another important term as it refers to whether the function opens upwards or opens downwards. If a critical point is concave up, it means it is a local minimum. If a critical point is concave down, then it means it is a local maximum. By finding these local mins and maxes, we can determine what x value gives the most optimal y value. For example, if a function were to model profit in relation to product produced, we could get the local max of the function through optimization. This local max would tell us how much product we should produce to get the maximum amount of profit, as any more or less product produced would result in the net profit being lower. In terms of the process of optimization, first you get the derivative of a function, and then the critical points of that derivative by setting it to 0. By setting the derivative to 0, we find where the rate of change equals 0, which indicates a possible extrema. We also have to check for where the derivative is undefined, as those could also be critical points. Then, by getting the second derivative of the function, you can determine whether each critical point is a local minimum, a local maximum, or an inflection point. This process is referred to as the second derivative test. If the second derivative is negative, then it's a local max. If positive, then it's a local min. If the second derivative equals 0, then it indicates a possible inflection point, which is neither, and the test is inconclusive, requiring intervals instead to determine what that point is. Euler's number, or E, is a mathematical constant used to model the growth and decay of many things, like bacteria or population growth. Technically speaking, it's used when the rate of change is proportional to the amount you currently have, like how bacteria increase more and more based on the amount of individuals you already have. This is also why it's called the natural exponential, as it's used to model the exponential growth of many natural processes. Its inverse is ln, or ln, which is really just log e x, and being a log, it is subject to all the log laws while also undoing e. This is because ln e equals 1, since log b to the same value of its base also just equals 1. And also, ln e to the x just equals x, which is another useful relation. One more thing of note is that the derivative of e to the x is still e to the x, which is a defining characteristic of this function. Though in cases where the exponent of e is more than just x, the chain rule must be used. These two can then be used to get the derivatives of exponential functions and thereby optimize them. So we will be evaluating this limit right here as it approaches 0. Now we actually have two separate functions that are being added together, and so because of this we can actually use a limit law to find the limit of these two functions together. The way we do this is basically by separating them into two separate limits that we will get, and then we'll add the limits together, which would then equal the limit of this overall limit here. Now for the first one we'll be evaluating this function right here, x5 sine 1 over x. Now for this one, since we have the sine 1 over x, right, we can't directly substitute 0 without dividing by 0, which is a no-go. And because of this, we actually have to use the squeeze theorem, since the sine function oscillates between -1 and 1 continuously, and so it never truly settles upon one value. And so because of this, we essentially have to trap the function and squeeze the limit out of it. Now, if you actually take a look at this x to the 5 times sine 1 over x, we can see that this x to the 5 multiplies everything in this sine 1 over x, which means that for this range, we can multiply all of this by x to the 5, which gives us this. Negative x to the 5 is less than or equal to x to the 5 times sine 1 over x, which is less than or equal to x5, x to the exponent 5. And so then what next we can do is we can evaluate the limits on both ends instead. Because if the limits on both ends are equal to each other, then the limit of the center one here, this here, must also be the same as the limits on both ends. So if we were to say it in terms of fx, hx, and gx, if this is fx, this is gx, and this is hx, if gx and hx are equal, then that must also equal fx, which would also equal the limit. And so we can evaluate it on both sides, negative x to the 5, when negative x to the exponent 5, when we get 0 is 0, and same thing on the right side here, which means that the center one, right here, must also be the same as the ends, which means that the limit of the center one must be 0. Now we have to evaluate the other limit and combine the limits together. Now limits, as said before, are basically just trying to find what value a graph approaches as we approach a certain x value, which is 0 in this case. But how we do that is basically by moving an indeterminate form like this. Like for example, if we substituted 0 into this right now, we would get a division by 0, which you're not allowed to do. And so then we factor, we multiply by conjugate bases and all of that, so that we can instead get a form in which we can substitute x in without breaking any of the math rules. And so we will be essentially simplifying this so that we can, and changing this form, the form of this equation, so that we can input the 0 in. Now the first thing we can do is we can actually use this little trick right here, where sine x over x actually equals 1. And so what we want to do is we want to manipulate this side right here, right? We already have an x, and then we have sine 3x, and we want to manipulate it so that the x on the bottom is the same as the x on the top. And how we can do that is by multiplying both the numerator and the denominator by 3. So we get 3x, which is then equal to the x inside the sine function, and then we also multiply by 3 on the outside there, so that the equation still is equal, since these 3's would technically just cancel out. And of course, since this is all multiplication, we could we've changed this so that it's this polynomial and these two terms, or these two factors, I guess, times this right here. And so this would simplify to 1, the sine 3x over 3x would simplify to 1, and then we just have a 3, which is right there. And then for this one, since it's a polynomial, we can actually factor this. And so we can remove an x immediately to get x squared plus 2x plus 1. Then we just factor to get x plus 1 times x plus 1, which then gives us this. And so we have x plus 1, x plus 1 times 3. And then, since there's already an x plus 1 in the denominator, we can cancel out these these two right here. So then we get this right here. And now, since we have square root or root in the denominator, we can rationalize the function to basically simplify it, and so we don't have a irrational number on the bottom, right? So we can rationalize it by multiplying by the conjugates to get rid of the root on the bottom, which then just gives us this form right here. And then we can just substitute everything in, since no math rules are going to be broken. 0, 0, 0, and 0. None of this is dividing by 0 or breaking any math rules, which then means that the limit is just 0, as you can see, because we're multiplying by 0, so all of this is just 0. And so then we just add the limits together, which previously was just 0 and 0, which then means that the limit of the overall equation is just 0. We will be getting the derivative of this function right here. X sine x squared equals y minus 1 over y plus 2. Now this actually includes many different derivative rules here. We have the product rule, since we're multiplying the x function by the sine function here as well. And we have the chain rule, because the sine actually multiplies everything inside its brackets, right? And so this would actually kind of be treated more as a chain rule, similar to how if we had a function to an exponent, we'd also have to use the chain rule there. Now since we also have y's, we also have to use implicit differentiation, and we have the quotient rule since we're dividing two functions as well. And so as you can see, you have to attach dy over dx to y prime, or every derivative of y that we get, we have to attach dy over dx to. Now I did this in terms of left-hand side and right-hand side, then combine the derivative at the end, just for ease of simplicity here. So we have this left-hand side, and so what we did is we got the derivative of this side right here, which the derivative of x is just 1. And then we have sine x squared, because we're using the product rule, which is this. And so we have sine x squared plus x, then the derivative of sine x squared, which is cos x squared, which is the derivative of sine. Then we have to apply the chain rule and get the derivative of everything inside the brackets, which would be 2x in this case. Then we have the right-hand side that we will now be getting the derivative of. Now for this, we have to use the quotient rule, which is this, and I will be walking through it here. So we have y minus 1, the derivative of which is just 1, since the derivative of y is 1, and minus 0, because the derivative of a constant is always 0. But since we're getting the derivative of y, we have to attach dy over dx. Then we multiply that by y plus 2, due to quotient rule again, then subtract by y minus 1, and then the derivative of y plus 2, which is 1 plus 0, which would just be 1. And since we're getting the derivative of y, we have to get dy over dx over y plus 2 squared, which is because this is essentially fx and gx. We have to do this. Then we simplify, as you can see here. And what we can do is we can basically divide both terms by dy over dx. That's what these kind of squiggly brackets mean. Not really brackets, just a way of denoting that we're separating the dy from this right here. And so we get dy times y plus 2 minus y minus 1. But then, since it's all just subtraction addition, we can combine the terms. And so we cancel out our y's, and then 2 minus negative 1 is just 3. So we get 3 over y plus 2 squared and dy over dx, which multiplies. Then we have this full derivative. And then we can solve for dy over dx. We bring the 3 down and divide everything on this side, and then we multiply both sides by y plus 2 squared, which then gives us this final derivative, which is now our dy over dx, or the derivative of this function right here. So now we will be finding the equation of the tangent for x squared times y squared plus 5xy equals 14 at the point 2, 1. So the first step in getting the equation of the tangent is to get the slope of the tangent, which is gotten through the derivative. And then once we get the derivative, we can plug in the point, which then gives us our slope. So the first thing we do is we get the derivative, which uses the product rule here. So you have the derivative of x times y squared plus x squared times the derivative of y squared, which, since we're getting the derivative of y, we also have to attach dy over dx, which obviously we just use power rule here. And then we also have to add it to the derivative of this term here, which is just 5, the derivative of 5x times y, which the derivative of x is just 1, so we just get 5. And then we add it to the derivative of y times 5x, which we also have to make into a dy over dx. Then we kind of rearrange the terms so that we can then pull out dy over dx from these two terms, which gives us this this factor right here, and then we have these two terms. Then we just move these two over to the right side, because we now want to solve for dy over dx, which is our derivative of this implicit equation. Then we just divide this side by this side to undo this multiplication, or we divide both sides really, but we kind of just cross multiplying. And so then we get the derivative, which is this. Then what we want to do is we want to get the derivative of this. Now we can simplify it, which when we simplify it, we realize that we actually get the two similar factors here, which then means that this is technically the slope of the tangent. Now we just plug in 2, 1 to get the slope, which gives us a slope of -1/2. Then we use the point slope formula so that we can get the equation of the tangent. We put in our y1 and our x1, right? Then we multiply 1/2, -1/2 by everything in the brackets, which gives us -1/2 x plus 1. Then we move this to the other side, or we add 1 to both sides, which then gives us this as our equation of the tangent. Y equals -1/2 x plus 2. Now we'll be solving this word problem right here. Find the dimensions of a rectangle with area 250 meters squared whose perimeter is as small as possible. This problem actually requires the use of optimization since we want it as small as possible. And so we will have to use derivatives and optimization to get the answer to this problem. Now we first have to define what our formulas are. Well, we have the perimeter formula, which is 2 times width plus length, since this is a rectangle. And then we have our area formula, which is width times length. Now we want to solve for one variable, which in this case I solved for w right here, so which is 250 meters squared over L. And then once we do that, we can substitute it into one of these formulas. And since we use the area formula to solve for the width, we substitute it into the other formula of perimeter. Then we substitute it in here. Then we have our equation, and then we just get the derivative of this equation, which kind of uses the chain rule here, or I guess the power rule, to give us our derivative right here. Then we have to set to 0 to find the critical points of this derivative. And then we set to 0, we just do some algebra, moving the 2 over on this side, because we subtract both sides by 2, we cross multiply, we divide both sides by 2 to get L squared equals 250, this is both these are negative. Then we square root L to get what L is, which is just the square root of 250. While I could simplify this, technically this isn't necessary right now. Now we have to find out whether this point is a local minimum or a local maximum. And we do that by getting the second derivative of this perimeter function here. And so we just get the derivative of the derivative that we previously found, which would be -2 minus 500L -3 plus 0, right? Or well, multiply both of these together, not subtraction. And which then gives us 1000 over L cubed. Then we just plug in the point we previously found, the L value, which then gives us a positive value, which means that this is a local minimum. So this is what we want, as this means that this is the smallest possible length that we can have. Then we just solve for W over here by using the area formula. We divide both sides, 250 over the root of 250. Then we kind of simplify, and then we get that the width is equal to 5 times root 10, which also is just equal to root 250, which means that both of these are equal to 5 times the square root of 10, and length is also 5 times the square root of 10. And this is the dimensions for the smallest possible perimeter of this rectangle, which truly just ends up being a square. And that's how you can use optimization to solve a word problem. We are just getting the derivative of this function right here, which involves an exponential functions, the constant e, and of course trigonometric functions as well. Now here are some of the laws we can have to use. For this one, for this term, we have to use the product rule, same for this term. But then we also have an exponential, so we have to use the exponential rule, and then the chain rule, and then we have the e and chain rule as well here, and here of course as well. So I did this in terms of terms, so the first term derivative, and then the second and the third term, just for the sake of simplicity. And then I combine it, and then I made sure to add everything together at the end. So for the first term, we have this as the derivative. Now remember, we have to use the product rule, which means we need to get the derivative of this for to the power of x function right here, which requires the use of this rule, which would also use the chain rule, but since the derivative of x is just 1, it's redundant to write it here. And so then you have this, then you have of course ln 4x, since we haven't changed that function. Then we have to get the derivative, then we have to continue using the product rule here, which is just 4 to the power of x, and then you have the rule for ln, which is this. And as you can see, it's 1 over x, right? But we don't have to remember to use the chain rule since it's within this bracket, and so we actually have a 4x, and so we have to get the derivative of 4x, which is just 4. Then we just simplify, and we get this as the derivative of our first term. Then for our second term, we have to again use the product rule, and so as mentioned before, one of the properties of ex is that its derivative is just itself. But since in more complicated cases, we'll have to use the chain rule, so I've also said 1 as that is the derivative of x if we were to use the chain rule, though technically not necessary in this case, or really just redundant, I suppose. And then you have times log 10 x squared as that's the second function. Then you just have ex again, and then you have to use the log derivative rule, which is this. And then again, you have to use the chain rule as well, and so you get 2x as the derivative, and then you just simplify, then you simplify again, and that gives you your second term. Now you have the third term, which thankfully is a little simpler, but you have the derivative of cos, which is negative sign, and then you have to obviously chain rule again, so you get 4x, and then you simplify, and so you get this. Then you add everything together, or you combine all the terms, and then you get this as your final derivative.